Let's have a look at this word problem. It says here, a searchlight on a yacht is being used at night to illuminate a sunken chest as shown. Here is the chest. At what angle of incident, theta 1, should the light be aimed? And here is theta 1. Looking at this sketch, there are two fluids here. Air is a fluid, so here is a fluid, air, and water. The interface between the two is along the surface of the water. Here is the light beam coming from the searchlight, and when it passes from one fluid into another, this light beam will refract or bend, depending on the index of refraction. In this particular case, since it's going from an index of refraction that is less than the index of refraction of the water, 1 being less than 1.33, the light will bend inward. Inward with respect to what? Well, it's with respect to this line here. And this line is called a normal. And it is normal with respect to the surface of the water, right here. And this is the point where the light will begin to bend, at the interface. Let me redraw this sketch down here. Here's the surface of the water. And the bottom of the lake or the lagoon where this chest is, down here. And let's see, I'll put the chest about here. And this is the important line right here. It's called the normal. And the normal is perpendicular to the interface between the two fluids. The top fluid here is air, and the bottom fluid is water. At the interface, this line right here is drawn perpendicular to this interface right here. And it's called a normal. Let's see, I'll write this word over here, normal. And normal means perpendicular. Perpendicular. So I'm drawing a line which is perpendicular to the interface between the two fluids, right here. That's what this dotted line represents. And theta 1, here's theta 1. I'm draw theta 1 here. I'm going to sort of exaggerate somewhat and make theta 1 going this way. And theta 1 is with respect to the normal sweeping outward. This would be theta 1, starting at the normal, sweeping this way towards the light beam. So you can see here it's sweeping out towards the light beam. And then the light is going to be refracted. Here, this one here sort of looks like it's going in a straight line, so I'm going to have to make a small adjustment. I'm going to put the chest here, such that it refracts inward. And this theta 2 is also with respect to the normal, sweeping outward this way. Starting at 0, sweeping this way, theta 2 this angle. So both of these angles are with respect to this normal, this dotted line right here. And we're given some other information here as well. Let's put these in. The depth that this chest is at 3.3 meters below the surface. And the distance from the normal to the chest is given here as 2 meters. The equation we're going to use in order to calculate this angle, theta 1, is known as Snell's law. Let's have a look at our equation sheet. And this is it here. Snell's law deals with the index of refraction. N1 sine theta 1 is equal to N2 sine theta 2. And the 1s and the 2s, they are arbitrarily given. So we'll call air, we'll call that fluid 1 and water fluid 2. That way, the index of refraction of air times the sine of the angle in air is equal to the index of refraction of the water times the sine of the angle in water. Call that 1 and 2. Let's write Snell's law here. Snell's law. And it generally states N1 sine theta 1 with respect to the normal is equal to the index of refraction of the other fluid, N2 sine theta 2, and that theta 2 again is with respect to the normal. We have some information, so I don't have to do a list of what is given. We've given N1 is equal to 1.00, and the index of refraction of water is 1.33. And where do these numbers come from? Well, they come from a chart. Here is a chart. And the index of refraction has no units. Different materials will have different indices of refraction. And the ones that we're interested in here right now is water, 1.333, and no units, and air. Now this will go to 1, 2, 3, 4, 5, 6, 7 significant figures. We're only interested in, we'll go to 3 according to this way the word problem is set up. We'll go to 3 significant figures for the units from this chart, or the dimensions from this chart. So water 1.33 and air 1.00. Let's put in some of the values that we know in our equation. N1 for air, 1.00. Sine of theta 1 is what we want to find. Is equal to N2. N2 is the index of refraction of water, which we already know is 1.33. Sine of theta 2. What we have here now is one equation, equation 1, but we have two unknowns. Theta 1 is an unknown, and theta 2 is an unknown. These two angles are unknown, and they are not equal to each other. This isn't like crossing a parallel line where the opposites are equal. So we need to find, well, we're asked to find theta 1. So we're find theta 1. We're going to find theta 1. So let's see if we can find theta 2 using a different method. Since we have one equation, two unknowns, this alone is unsolvable. So we need to find this using a different method. Let's go back to our sketch. Here's theta 2, and we're given some dimensions, 3.3, 2 meters this way, and this line being the normal is perpendicular to the surface, and we'll assume that the bottom of the ocean floor is also perpendicular to the surface, so that is perpendicular here. And what we have here then is a triangle. Let's draw that right angle triangle. And that distance is 2 meters. This height is 3.3 meters. Theta 2 is what we want to find, and we know this is right angle. Being a right angle triangle, we can use SOHCAHTOA. Looking at this, here's our angle. We have an adjacent and we have an opposite, so we're going to use tan. Tan theta, tan theta 2, is equal to the opposite divided by the adjacent. Adjacent. Here's the opposite, and this is the adjacent to the angle that we are interested in. Putting in the numbers, tan theta 2 is equal to, well, the opposite is 2 meters divided by 3.3 meters. Yeah. Meters will cancel out. Now we need to find the angle. To do this, we're going to take the inverse of both sides, the inverse tan, and that will result like this. Theta 2 is equal to tan to the minus 1, the inverse of tan, times these two numbers, 2 divided by 3.3, and the meters cancel out. Putting this in our calculator, let's have a look. We go tan to the minus 1, second function, we'll find tan. Tan to the minus 1, open that bracket, 2 divided by 3.3, close that bracket, is equal to, there's our number. And it's in degrees, 31 point, because I have this set for degrees, 31.218 is equal to 31.2184. And in this case right here, let's round this to, these were two sig figs, we're going to round this to 2 sig figs. Theta 2 is approximately 31 degrees. Now we'll carry on with the 31.2184 degrees. But we'll use this number, remembering that we're using two significant figures here for the final answer. Now that we know what theta 2 is, we'll go back and we'll use theta 2. Putting in the numbers here, we have 1, well, we won't bother writing the 1 down, so it's sine theta 1 is what we want to find, is equal to 1.33. Sine of the angle of theta 2, which we just found to be all of these, 31.2184 degrees. Let's find out what this number is. Sine theta 1 is equal to, well, I already have that number here, 31.218. I just need to take the sine of this number and then multiply by 1.33. So let's see, sine equals times 1.33 equals sine theta 1 is equal to 0.689341. In order to find theta now, I need to take the inverse of this, the inverse of sine. Sine to the minus 1 of sine theta is equal to sine to the minus 1 of 0.68934. This turns out to be theta is equal to sine to the minus 1 of 0.68934. That number is already here. So we'll take the inverse sine. Inverse sine. Where's sine? There we go. Is equal to 43.57. And this will be in degrees. Now looking for sig figs. We go back to the original question with all the values that are given to us, and we see these are two digits. Here we have 3 digits, 3, 3, 2. As I mentioned earlier, we're working with two significant figures here. So the least number of sig figs here in our original word problem is 2. So we're going to reduce this to 2. Sine theta 1, approximately 44 degrees. And this 44 degrees, and here's the surface of the water, is with respect to the normal, sweeping this way. That'll be 44 degrees, sweeping that way.